We're very happy to have Sujay Ashok from IMSC Chennai, and he will tell us about surface operators, dual quivers, and contours.
Thank you, and thanks to the organizers for such a nice meeting and for asking me to present my work. So to the math people in the audience, I have to apologize. I don't have much for you, and that's not because that's not a choice. It's because I don't know much math. So this is a sort of large N project in the sense that a lot of people involved in the collaboration. This is mostly based on the paper that came out last week, but it builds upon some earlier work on surface operators. And a good way to think about this series of papers is as a follow-up, if you wish, to this paper by Kyoto, Gukov, and Seiberg that came in 2013, called Surface Defects and Resolvents. So part of what we try to do here is to clarify and extend much of the ideas in this work. Okay, so let me start with a very broad context. In a general quantum field theory course, a lot of time is spent trying to learn how to calculate correlation functions of local operators. We're going to extend that to include extended objects such as line operators or surface operators and so on. And over the last decade or so, there's been a lot of progress in trying to calculate these observables exactly in the coupling constant using so-called localization methods, beginning with the works of Nekrasov and Peston and so on. So in this talk, I'll mostly focus on a very simple sort of calculable quantity, which is the Instanton partition function in a supersymmetric gauge theory in the presence of what is called a surface operator. I'll define what that means in a moment. And in the math literature, this is referred to as the Ramified Instanton partition function. And for all of this talk, except maybe the last slide, I will just study pure n equals 2 gauge theory with no extra matter. And this is the theory that has been studied 20 years ago, well, more than 20 years ago by Seiberg and Witten, and also studied again using methods of localization by Nekrasov. So this is the main quantity of interest, the partition function in the presence of surface operator. Okay, so another general slide about defects in general. So there are many ways to study defects. The first way is to describe how the defect affects the bulk gauge theory. So you specify how the bulk gauge fields are singular at the location of the defect. So a classic example is the 't-Hooft operator in ordinary gauge theory. So the first thing we'll do is to describe surface operators as a kind of defect in this language. Another way to describe a defect is to specify what additional degrees of freedom is being coupled to the four-dimensional gauge theory. So in this context, we will see that there is a description of surface operators as a two-dimensional quiver theory coupled to the four-dimensional gauge theory of interest, which will just be a SU-N gauge theory. And lastly, and sort of democratically, one can realize all of these things using D-branes and string theory, both the four-dimensional gauge theory, the defect, and everything. But I will not have anything to say about this in this talk. So we'll mostly focus on these two ways of describing the surface operator. So as you can see, the intersection of all these names is actually in the audience. So if there are any detailed questions, we can also ask his help. So the plan of the talk is as follows. There are 3 sections. In the first section, I'll describe surface operators as monodromy defects. And this will be a very sketchy sort of section where I'll just try to describe how one writes down the partition function in the presence of the surface operator as a contour integral. And the main goal of this section will be to ask a particular question, and that will be to understand a particular calculable quantity, which is the low energy effective action, in a more physics language. So most of the talk will be here, the second section where I'll describe the physics of surface operators, or the low energy physics of surface operators as a coupled 2D, 4D quiver gauge theory. And we'll spend some time trying to exactly map quantities on both sides of this map. The last part of the talk will be to go the other way. Now that we have this description of surface operators as a coupled 2D, 4D theory, there is a particular operation one can do in the two-dimensional theory, which is called Seiberg duality, where there is nothing one can do, it's an equivalence class of gauge theories, and all of these theories are supposed to flow to the same infinite theory. So the question will be, how is this Seiberg duality operation in this original description surface operator as a monodromy defect? So basically, we have questions to answer, which I can't ask right now because I have to first describe the first section. I'll try to highlight why those two questions arise. So are there any questions about the general setup? If not, let me describe surface operators as monodromy defects. So this is work of Gukov and Witten. And as far as we're concerned, we'll always describe surface operators as a sort of two-plane inside the four-dimensional space where the four-dimensional gauge theory lives. So these are codimension 2 defects in the four-dimensional gauge theory. And the defect is described by specifying that the gauge field, the four-dimensional gauge field, has a specific profile at the defect. So maybe it's good to draw something here. So if this is the two-plane transfers to the defect, which is here, then as r goes to 0, which r is the transverse distance from this two-plane, A takes this precise form. And this is singular because the field strength has sort of delta function source at the location of the defect. And these alphas are real parameters, such that we still have an SUN gauge field, and these n's are just a partition of n, capital N, the gauge group. So if you want to do quantum field theory with this defect present, the idea is to do the gauge field path integral provided you specify this singularity at the location of the defect. So at the defect, the gauge group is broken down to this subgroup, which is a Levi subgroup of SUN. And this is the description of the defect as a monodromy defect. And so the claim is that for every partition, there's a surface operator. But because you have a surface operator, and one can turn on magnetic fluxes for each U1 factor in the Levi subgroup. So if I go back a moment, there are M U groups, UNI subgroups here. So for each one of them, one can turn on a magnetic flux along the defect, such that the overall U1 decouples because you have an SUN gauge theory. And in addition, because my defect is two-dimensional, I can also turn on a topological theta term in the path integral. So the data of the defect consists of a discrete part, which is just the partition of n. And in addition, we have 2m real parameters. So alpha, if I go back a moment, are these parameters here that specify the profile of the gauge field at the defect. And eta are these theta parameters. So this is the data of the defect, and what you're asked to do is to calculate the Instanton partition function in the presence of such a defect. Right, so let's sort of recall for a moment what happens without a defect. So without a defect, the partition function is weighted. You sum over Instanton sectors, and each sector, which is labeled by k, an integer, is weighted by e to the minus action of the Instanton, which happens to be that. So the partition function is written as a sum over Instanton sectors, like so. Okay? So I haven't told you how to calculate zk, but this is sort of the form of the Instanton partition function. But already from what we've discussed, we can see that there are several changes. First of all, we have a theta term in the path integral. And then we said we introduced magnetic fluxes when I sum over magnetic fluxes. And lastly, as we'll see, the presence of the defect will modify the weight factor as well. So let's try to see how, at least, even if I don't tell you how to calculate these, let's try to understand what is the weight factor that corresponds to an Instanton in the presence of a surface operator. Okay, so this is what I mentioned, that the topological action now consists of two pieces. One is the FHF piece, which is always there, and this is the extra piece that comes from the two-dimensional topological term, and this is just eta I mi. In addition, in the presence of the defect, one can show that this FHF term, in fact, contains two contributions. It contains the usual Instanton number and contributions that come from the defect. So if you put it all together, one can see that the topological action has this form. We just had this earlier, but now we have a contribution that comes from the magnetic fluxes. And this T is the complexified parameter eta plus tau alpha, where tau is the complexified gauge coupling of the four-dimensional theory. So the claim is that instead of that, which we had earlier, now we have something like that. So we have, so I'm just putting this e to the minus s topological as the weight factor of the partition function. And just as there is a way to calculate zk earlier using equivariant localization, the claim is that there is now a way to calculate this. There's some black box that tells us how to calculate this z for every zk. Okay. Are there any questions to this point? The most general?
Yeah, so you gave
Yeah. Yes, yes. No, so the claim would be that they are equivalent descriptions. I can use either one to describe the defect. And at least as far as the low energy action is concerned, you get the same thing. But, okay. In this language. Okay, I see. I had not thought about it. Okay. Okay, so at this point, we have a sum over instanton sectors and the magnetic fluxes. The claim is that one can, by a change of variables I've mentioned here, rewrite it as so, where each di is now a natural number. So this is not obvious, but it's possible to do so. And this z di is what is usually called the Ramified instanton partition function. And these are the weights of the ith factor in that expression. And we'll see a sort of physical interpretation of what these QIs are in terms of vortex partition, vortex actions later on. But one thing I'd like you to notice is the following, that with this redefinition, the product of all these QIs is what I would call, what I had called a one instanton term in the case without a defect. Capital M, it's sort of the number of factors you had. Yeah, exactly. So you take a partition of I going from 1 to M. Okay. Right. So let me just show you one slide as to how one might calculate those ZKMs. So it was shown by Kano and Tachikawa that this what do I call it? These ZDIs, as I call them here, can be calculated using equivariant localization. And the idea is to describe the moduli space of instantons with surface operator as an orbifold, a ZM orbifold, of the moduli space of instantons without the surface operator. So it's not at all obvious why this should be so. But if you're given this definition, and if you're a string theorist, what one can do is to study in this background the dynamics of open strings with at least one leg on the D instanton. And the D3s will realize the four-dimensional gauge theory. The orbifold knows about the defect, and the moduli action of the D instantons will give me exactly this guy. Okay. So I've introduced here these epsilon 1s, epsilon 2. These are the usual omega deformation parameters that regulate the volume of the moduli space of instantons. And we will always be on the Coulomb branch. The only difference now is that now the Coulomb webs also have to be split into this partition into M sets. And there are exactly ni of these in each set. And so at the end of the day, what one would find is a power series expansion in these new ramified instanton weights, some rational functions of A, epsilons, and whatever mass parameters you might have in your theory. And this boxed partition function is what one would calculate using equivariant localization by order. Okay. So this is all fine, and I haven't told you how to do any calculation yet. But so suppose someone gave us this, what could one calculate? Well, the claim is that in the limit of vanishing omega deformation parameters, partition function is singular, as expected, and the singularity is of a very particular type. First of all, you can check that so this f is the usual prepotential of the four-dimensional theory, and one can check that no matter what defect you take, the f that you calculate is always the same, which is good. So you're always in the same four-dimensional gauge theory. And now you have a sub-leading singular piece, which is this what I call W instanton as well. W depends not only on the Coulomb waves, it depends on these other parameters I mentioned, the QIs as well, not just on the product. And we identify this with the infrared, yeah. Yeah, so epsilon 1 is along the defect and epsilon 2 is perpendicular. Along the defect. Yeah, so this is what I was trying to say here. So we identify these with the four-dimensional and two-dimensional theories respectively because of this, the fact that the super volume of the regulated C2 or C goes like that, exactly. So in the limit of epsilon goes to 0, they go to infinity. For finite epsilons, these are the volumes of the, if you wish, the one instanton terms. Okay, so the claim is that the F instanton captures the low energy dynamics, the low energy effective dynamics of the four-dimensional theory, and W instanton captures the dynamics of the two-dimensional theory, somehow still coupled to the four-dimensional theory. And the first question that we'll ask is, how can we understand this from a more physical perspective? So for instance, if you take the simplest SU2 and you do this procedure of these ramified instantons, what one would find would be this. So at leading order, if you just look at one instanton, W would look like that. That's it. So in general, it's some power series in all the Qs. And what I'll spend most of the next hour doing is to explain how to capture this, or to understand this from a more physical perspective. Okay. Are there any questions so far? Comments? Okay, and let's move on to the next topic, which is to describe surface operators as 2D, 4D quivers. So the main claim is that if you want to describe the surface operator of Levi type L in SUN, one way to do that is to study the sigma model on this target space. So I should have mentioned Kannon Tachikawa as well here. So the low energy dynamics of this should tell us something about the W function we saw earlier. So for this case of interest, where L is this UN1, UN2, and so on, this is a flag manifold. And since the defect is half VPS and preserves 2,2 supersymmetry, there is an equivalent description of this, sort of ultraviolet description of the sigma model as what is called a gauge linear sigma model. So this figure it represents the following. So each node is a URI gauge group. Each arrow describes a bifundamental matter multiplet charged under these two gauge groups. And this funny looking N is the SUN gauge group we started with. So from the two-dimensional point of view, this is just a flavor group. It's a global symmetry of the two-dimensional theory. But as we'll soon see later, we're going to turn on the dynamics here in a very specific way. So we haven't told you how to couple the four-dimensional gauge theory to the two-dimensional quiver. So what I'm going to do next is to tell you how to study the low energy physics of this 2D, 4D coupled system. Okay, so I'll just summarize briefly how we go about it and then show you in an example how to do it. So once you're on the Coulomb branch of the four-dimensional theory, the SUN is broken to U1 to the n-1. And from the 2D perspective, the Coulomb waves of the four-dimensional theory play the role of twisted masses. I'll try to explain what that means in a moment. So the physics of the low energy theory is the following, that all chiral multiplets, which means all these arrows all these bifundamental matter multiples, all of them are massive. What we'll do is integrate them out. I'm not going to do this exactly. It's one loop exact. And so we have an effective theory of vector multiplets in 2 dimensions. So gauge fields in 2 dimensions. And with 2,2 supersymmetry, what one can show is that the entire low energy effective action is encoded in a single holomorphic function, which is called a twisted chiral superpotential. So because the theory is massive, the vacua are obtained by extremizing the superpotential. And the massive vacuum means that there are a finite number of solutions, finite and discrete solutions to these equations. Okay. One could, but I'm not doing that. I'm at a generic point in the Coulomb moduli space. It would mean tuning the Coulomb waves in some way, I guess. The 4D waves in some way. Yeah. Yeah. Could that be related to your question? Maybe. Yeah. I don't know. Related, okay. Okay, but we'll just work with generic Coulomb waves, so the whole theory is always massive. So this is a set of vacua. And the claim is the following: there's a one-to-one map between the massive vacua of this 2D, 4D theory and surface operators. In particular, if you evaluate the twisted chiral superpotential on the minima or the extrema of this chiral ring equations I showed you earlier, the claim is that that coincides with what we calculated, what we calculated using localization. So this is a precise map between what I said in the beginning, what I said using this new description. So the evaluation of the twisted chiral potential on the massive vacua is W Instanton. So the real question is, what is the map between, how do you relate the massive vacua one to the other? But if you just want the non-perturbative pieces, so if you just want the instanton piece, you can fix that without that. You can. So let's see how this works in the simplest example. I take the SU2 theory and take the only defect there, which is defined by the partition 1, 1. So let's go back a moment and look at this quiver I drew. So you see that these ranks are determined by the partitions. So these ranks are increasing each time you add an extra n to this 2D ranks. So in the case of the SU2, there's only a single one I can write down. This n is 2, and I can only write 1 here. So the 2D gauge theory is just U1 gauge theory. And so what we have to do is to study this system. So for the purely 2D theory with SU2 flavor symmetry, the effective potential has been known for a while. So here I've already integrated out the massive chiral multiplets, and the effective potential is just this form, sigma log sigma. And this first term is the complexified phi Teleopoulos coupling of the 2-dimensional node. Okay. So if you had SUN here, I would have put n instead of 2 here. So it's very simple to generalize. So what we asked to do is to take this and to extremize. But now let's see what the twisted masses will do. So what the twisted masses does is to add this term to the superpotential. So instead of sigma log sigma, sigma gets shifted by the twisted masses. But as I said, twisted mass is nothing but the Coulomb waves of the 4-dimensional theory. So this is what we get. But in the fully quantum theory, we have to understand how to couple the fully dynamical 4D theory to the 2D theory. And the proposal by Gayatri Gurkov and Seiberg was to calculate, to put, treat this as a chiral correlator in the 4-dimensional theory. So here, this would be the classical waves. Here I have a real quantum operator in the 4-dimensional theory. Okay? And this is related to the resolvent, because the resolvent is the generating function of all chiral correlators in the 4D theory. It's defined as trace 1 by sigma minus phi. And if you do a double integral of this, you get this function. Or take 2 derivatives of this, you will get this function. Okay? So somehow this coupling knows about, knows about all chiral correlators of the 4-dimensional theory. So if you know the resolvent of the 4-dimensional theory, you can write down the effective action of this U1 theory coupled to the 4D SU2 theory. Here we can fix by looking at the asymptotic behavior for large sigma, for instance. So if you integrate this, and you say, so if you integrate this, you want to find trace log sigma minus phi. If you know the large sigma behavior, which you do, you can fix the constant of integration. I can try to show you how to do this. Yeah. Anyway, so I would say, right. So let's see how this works in practice. So this is what we had in the previous slide. Now what I've done is to introduce the dynamically generated scale in the two-dimensional theory. Well, this is the proposal. I think a later paper by Lefloc, Gorski et al., they sort of showed how this appears in the limit of vanishing omega parameters by starting with the correlation function in the partition function itself. We can discuss that afterwards. But I think maybe you have a comment. But yeah, I think in their formulation, they have the expression value in the partition function, and then they take a limit of small epsilons, and they get this as the sort of semi-classical answer. Okay, so here I've introduced the dynamically generated scale, which is lambda 1, and it's related to the exponential and exponentiated and running phi to Laplace coupling of this U1 theory. So the chiral ring equation is simply that. So if you know trace log, you can try to write down the chiral ring equation exactly. And this problem of solving for the resolvent of the 4D theory in the pure case was solved by Cachaso, Douglas, Seiberg, and Witten, I think in 2002. And this is what it looks like. So the resolvent is written in terms of the Seiberg-Witten curve. So the geometry of the Seiberg-Witten curve of the four-dimensional gauge theory enters the resolvent of the 4D theory. And so now we have an exact function now. So trace log is some function. And this gauge polynomial P is the quantum corrected gauge polynomial. So we need to know what this chiral correlator is in the four-dimensional theory. And this is the form of the chiral ring. So you can see that there are two solutions. You can have plus or minus, but that's just a wild reflection. So both of them lead to the same surface operator, roughly speaking. So sigma star is a solution of the chiral ring, and you can write it as a semi-classical expansion in all these strong coupling scales. And notice now that because of the resolvent involves the 4D coupling, this involves the 4D coupling, the 2D coupling, and everything else. Okay. So this is sigma star, and now I evaluate the superpotential on the solution. I extract the one instanton piece, the leading term, and I see compared with what I had earlier. And I see there is a perfect match, provided I make the following map between those ramified, the counting parameters for the ramified instantons, and the strong coupling scales of the 2D 4D theory. Okay? So provided that I make this map between Q and lambda, there's a perfect match between the two. Okay, and this lambda 1 square is, I want to just comment that this is the sort of the e to the action of the vortex solution in 2 dimensions. No, it's more. It's the set of all chiral correlators, in some sense. Yeah, but the result is written in terms of the, I mean, you see, the curve only has U2 to UN, in some sense. Whereas the resolvent tells you what is trace phi to the 100, for instance. And it's not just derived from an n by n matrix. The quantum chiral ring is not just the classical chiral ring, in some sense. The ring is modified. So if you expand this on both sides for lambda 4D, right? You will see that the trace phi to the 100 is not just obtained from the lower traces. There are genuine quantum corrections that you can't see beforehand. No, this is the quantum. So this is different. This is the quantum chiral ring, and they got it by solving this Konishi normal equations and so on. So. Are there more questions or comments? So this is the case for the simple SU2. Now let me tell you the solution for the generic case. So here the key is to understand what is the map between the surface operator and the massive vacuum. So which massive vacuum corresponds to the surface operator we started with. So the first step is still the same. I can integrate out each of these bifundamentals, and each of these bifundamentals will give me this sigma log sigma term. So this omega bar is just this x log x function I had earlier. So for each of these, I have a corresponding effective term in the action. And for the last guy, for the last chiral multiplier that goes to the 4D theory, I have this modified coupling by the resolvent. The twisted chiral ring equations can again be written down for each of these sigmas for each node in the 2D theory. And again, one can check that all solutions are discrete. There are discrete solutions, but what is the map to the surface operators? And what helps us is to understand that in the localization calculation, I had to make a choice for the split of the Coulomb waves into m distinct pieces. And the form of the quiver gives us a very natural classical solution to these equations, which is this embedding. So if you have, so these R's, remember, are successive sums like that on the board of n1 up to ni. So as a classical solution for these sigmas, we choose the first I blocks. So it's a natural embedding of one into the other. And the claim is that if we solve the quantum chiral ring equations at physical vacuum order by order in the strong coupling scales, then that reproduces for you the Instanton expansion that I showed you at the beginning with this split of the Coulomb waves. Okay? So this is what I'm saying here. So you can solve the chiral equations order by order in the scales about that classical vacuum. And that reproduces the Instanton partition function, provided we make the following map between the counting parameters on the localization side and the strong coupling scales of the 2D, 4D theories. Okay. And this we have checked for numerous cases, and it works. So are there any questions up to this point? If there isn't, let me just summarize this in form of a table. So here we had some partition of n, and that determined the ranks of the 2D gauge nodes. Then we had a split of the Coulomb waves because of the defects. The 4D Coulomb waves mapped to the 2D twisted masses, as we saw. And the partition of the 4D Coulomb waves is what gave us the choice of classical vacuum about which we solved the quantum chiral ring equations. And lastly, the Instanton counting parameters map to the strong coupling scales on the 2D and 4D quivers. And then the W Instanton is just the evaluation of the W sigma on the particular vacuum we chose. Yeah. Yes, but when we wrote down the localization integral, we need to make a choice there. I'll show you in a moment how that comes about. You need this choice. You need this choice of split of the Coulomb waves into these Ni blocks. Yeah. Yeah. It's essentially because of the ZM orbifold. So ZM orbifold acts on both the D3, part of the D3 and the, so anyway. Okay, so far I've been very lax about the localization side. I just said, oh, there is this black box that gives us the answer. So let's see what it looks like. So this is, for instance, the one Instanton contour integral, and you're supposed to choose a particular set of poles. You're supposed to choose one pole in chi. You're supposed to give some prescription to choose some set of poles, given the integrand. And the usual way one does this is as follows. We assign a real part 0 to the Coulomb waves. And we assign a positive imaginary part to the omega deformation parameters in a particular way. And then we say either the contour is chosen in the upper half plane or the lower half plane. That's a very simple way to specify the contour at one instanton. So because there is no residue at infinity, one can see that whether we close the contour in the upper or lower half plane, it makes no difference. But the poles that are chosen are different. Okay? So for instance, what one can check is that if you want a term-by-term match with the solution of the chiral ring, the contour one has to choose is the following. You have to choose plus, all pluses except the last one, which has to be minus. So what that means is that you take this integral, so there are m, so it's a sum over m terms. So for chi1, we choose all poles in the upper half plane. So we choose the ni contributions to that contour. And this is true for all m minus 1, except the last one, where we choose nm plus 1, which is n1. Okay? So my claim is that if you want to mask the superpotential term by term, then the contour that matches what we solve from the chiral ring is actually this one. Okay? This is what I've said here, but of course at higher instantons, we can't just say if it's an upper or lower half plane, we have to specify the contour in more detail. Either we have to specify some order in which we do the chi integrals, or we have to do it in some other way. And the way to do that is, so this is the higher order, this is the integrand, if you wish, at arbitrary instanton order. It's some rational function with a prescribed set of poles. And the way to specify what factors in the denominator are chosen by your contour is most succinctly specified by what is called the Jeffrey-Kirwan residue prescription. So what you do is to specify a reference vector, which I've called like that, and your integrand has some number of denominator factors, and the number of factors is more than the number of poles you need to specify always. So what you do is to choose some set of denominators, and the claim is that the reference vector is chosen such that the positive linear combinations of these should give you the chosen reference vector. Okay, this is a really ham-handed way to say it, but so let me study so consider the following integrand. All integrands, all factors here, you can forget the omega deformation parameters for this purpose. All factors here are either plus or minus chi I, or they begin with chi I minus chi j. So you choose the appropriate number of factors you need to specify the integral completely, such that a positive linear combination of these gives you the chosen reference vector. So this selects a certain set of poles, you calculate the residues at those poles, and that's your partition function. Okay? So what I just told you earlier about the all pluses and all minuses translates to this statement here for the choice of reference vector. I've multiplied these chi's by arbitrary positive real numbers with a prescribed ordering. So with this choice, you can check there's a term-by-term match between the superpotentials calculated by localization and by the twisted chiral ring analysis. Okay? And I'm going to identify these zetas with the phi Eliopoulos parameters of the 2D nodes. Okay? And what this translates to is a hierarchy of scales in the 2D 4D quiver. So we're just sort of saying that we cannot decouple this node unless we have decoupled this node first, and so on. So there's a specific sequence in which we decouple the nodes of the 2D 4D quiver. Okay. So that requirement translates to this coefficients that appear in the Jeffrey-Kirwan reference vector. Are there any questions or comments at this point? Okay, so far, I've just worked with the oriented quiver. So let me reflash for you the result we had with just this addition in blue, where now I'm going to say that what we have shown is that the oriented quiver, which means that all the arrows point the same way, maps to this particular choice of contour on the localization side. Okay? But now let me ask the second question that I promised, which is that there is nothing sacred about the oriented quiver. One can do a duality on any of the 2D nodes by a 2D Seiberg duality that will transform the gauge groups, the matter content, everything. And all of them should give you the same infrared physics, which is all we're interested in. So now we ask the question, how do you understand these possibilities, these dual quivers, from the point of view of localization? Okay. So let me briefly summarize Seiberg duality for you in 2 minutes. So essentially, we start with a 2D UR gauge theory with some number of anti-fundamental and fundamental matter. And we do an operation where we dualize this node to get a different node. So this is a max of NF and NA minus R. For simplicity, I've chosen NF greater than NA. So the arrows change directions, and we get a new field, a mesonic field, attached to these two flavor nodes. And in addition, you have to add an ordinary superpotential term as well in the action. And as far as the twisted potential is concerned, what happens is that the phi theta plus parameter of the dual theory is opposite that of the original one, and we get an extra term that depends on the twisted masses of the fundamental. Okay. So that's it. So this is the basic move, and we have this oriented quiver. In principle, we can apply this duality operation to any of the nodes. Okay. So for instance, if you had a quiver and we decide to dualize this, we notice that not only does the phi theta plus parameter of the node being dualized flip, the Fi parameter of the adjacent node also shifts. Okay, so Seiberg duality acts on the phi theta plus parameters of all these nodes, particular way. On the other hand, if you have a sort of chiral node where you only have outgoing matter, then we see that the phi theta plus parameters of both the nodes are affected. This is a simple consequence of the basic move. And so now we can just act with this move on our oriented quiver and see what we get. So this is an example of a duality chain where I start with the oriented quiver. I end up with the oriented quiver in the opposite direction. And in between, we only go through linear quivers with no loops. So loops are avoided if you always dualize nodes with only one kind of matter coming out. So we can just do that by being careful. But we don't have to do that. We can also do other chains. Again, the start and end points are the same. But you go through all sorts of loops and everything. And the question is, what are all these things from the other point of view? OK. Right, this is what I've already said, that all of these should describe the same surface operator. And the question is, and the point is that the Seiberg duality is an infrared equivalence. So the superpotential evaluated on these vectors should also be equal. And this is the real hint. So we suspect that the different dual quivers should correspond to different choices of contour on the localization side. So I showed you a big integral, and we chose a very particular contour to get the oriented quiver. And what we want to say is that if you chose a different set of poles that were chosen by a contour deformation to an equivalent contour, then somehow one should be able to see the ranks of these dual quivers. Okay? So one has to not just look at the overall potential, but one has to look at the residues themselves, and we can try to reconstruct from the individual residues the solutions to the chiral ring equations. And this is indeed what we see, effectively. If you don't buy this, in the sense, if you think this is not convincing, that maybe individual residues don't mean anything, I will show you at the end that if you generalize the problem to SQCT, we can clearly see that different contours give you different results. So maybe at the end, you can ask me again. All right, so, but even if you didn't suspect it, one could just work constructively. One could take one of these quivers I showed you in the chain and just did what we did for the first quiver. We could just integrate the matter out, write the chiral ring, find the classical vacuum, expand, and just see what we get term by term. But of course, there is an easier way to get this map, so let me briefly describe how we would try to get the map between quivers and contours. Okay, it doesn't come out very well. I hope you can see this. This is just the chain I showed you earlier. And I've written next to it the classical potentials for each of these cases, starting from the first one. And I've written each of these in terms of the Fi parameters of the original one. Okay, so at the end of the chain, note that 3 has become the coefficient of sigma 1, and 1 has gone there. There's a sign flip and everything. So there's some action on the Fi parameters by the action of Seiberg duality. And the claim is this is sufficient to give us information about the contour. So what we say is that the classical webs are very easy to describe for a particular, so the map between the classical web of one quiver and the other is simply obtained by taking the classical superpotential and just equating it. So you just equate WQ2. So you see, you start with WQ1, which was something like T1 trace sigma 1 plus T2 trace sigma 2 plus and so on. And W2 is that, right? We know what the classical webs here are going to be, because we figured that out already. It's the inclusion. And so we can just read off what these classical webs of the dual quiver is by just equating at the classical level this superpotential. So that gives us the classical vacuum. Then the action on the phi Laplace parameters automatically gives us the map between the counting parameters that we had in localization and the strong coupling scales of this new theory. So I'm calling these still lambdas, but these are the lambdas of this new quiver. Okay. And now you see that it's not just the second lambda to some particular power. We see ratios of scales appearing. Okay. So once these two are known, our claim is that there's a very simple way to write down the Jeffrey-Kirwan vector, reference vector that corresponds to a particular quiver. So what we do is to associate to each of these 2D nodes a particular chi integral. So we associate this one-to-one map between chi integrals and the sigmas that appear here. And these scales are always assigned in this particular order. And what we find is that if you write down the general vector, write the general vector here, y. So the general vector would correspond to a sum over I of sine of the beta function times zeta alpha I chi alpha I. Okay. That's it. So these zetas are ordered according to this. So which zeta appears here depends on the association between the 2D node and the chi integral. So I haven't been very precise about that, but the details are in the paper. But the point is, there's this very simple way to write down the Jeffrey-Kirwan vector given the form of the 2D quiver. And if you do that, we find a term-by-term match between the twisted potential calculated in the two approaches. And we've checked this for all the quivers I showed you in the duality chain. So these are examples of various different quivers and the associated Jeffrey-Kirwan reference vectors. Okay. And sometimes, so in the case of Q2 and Q3, we'll see that it's the same reference vector. It looks exactly the same, except that the ordering of the zetas are different. So that is enough to select a completely different set of poles in both cases, and the answers you get will be different. So now we can add another line to this dictionary, which is that the choice of contour maps to a particular duality frame in the 2D, 4D side. So let me conclude with some remarks, which is that it would be nice to understand from first principles why the particular ratios of scales appear in the 2D theory. At the moment, we're trying to do a string analysis of this whole setup to try and better understand all these features, including, I mean, this statement is like saying that your ramified instantons are described by fractional branes, and if you combine m fractional branes, you get a gauge instanton, essentially. So this is what I alluded to earlier. If you do the same problem now, not for the pure theory, but for the conformal theory, then what one can show is that if you choose these different Jeffrey-Kirwan vectors, then the superpotentials themselves are different, but the superpotentials match those that we calculate for the appropriate quiver. So let me give you a pictorial version of this. So these are 4 of these. So this is a 3-node duality chain, but now I have added flavor. So these are flavors for both the 4D theory and for the 2D theory. And we again do Seiberg duality. Now if you evaluate W on the massive vacuum, they're all different. And yet, there's a one-to-one map between what we calculate from this quiver and the corresponding Jeffrey-Kirwan vector. So the W is evaluated, yes, I would say yes. So it's because there is a residue coming from infinity. Because for conformal SQ3, there is a residue in infinity. And what we're trying to do now is to try to understand how that's consistent with Seiberg duality. Because now the rules are different for conformal SQ3, the Seiberg duality rules are different. One has to show that it is consistent with Seiberg duality. I'm saying those distinct answers match each of these. If you just calculate yeah, so, but yeah, we're trying to see how this is consistent with this 2D Seiberg duality at least, to try and see. So I think I'm done. Thank you very much for your time. Yes. No, it's the same separator. So the total superpotential will be the same, but it's just that the two descriptions are the same if you do a contour deformation. So just that was the sentence. Sorry. Let me see. The conformal case. Oh, here you mean? Not this one. Then I might have made mistakes. Then let me see. Here. So this is just the localization approach and the 2D 4D approach. So I'm saying you can just see the poles that contribute to a particular contour by solving the chiral ring of a particular quiver. That's all I meant. Well, we found a failed duality. I'll tell you what I mean. So if you now, so you see, here I dualized this node. If I dualize the node that attached to the flavor, then what we find is that there'll be a loop that goes from here to the flavor. So there'll be 2 arrows coming to the 4D flavor. And for those cases, there is a mismatch between what I would naively solve for the 2D 4D quiver chiral ring and the corresponding, what I would think is the contour. So I suspect that one would need to modify, because this involves the 4D node, I suspect that I would need to modify the basic 2D duality move to include some 2D 4D move to make that work. But we haven't done that yet. Yeah, that's a good question. Yeah. Yes. Okay. Oh. I agree. Yeah, one could do that. I agree. I don't know the answer, but yeah, one should do that. Probably. Well, another comment that I should say is that, where did it go? I think this is something I discussed with Satoshi earlier, that there is no quiver for the all pluses. He was very bothered by that, but so the all pluses are what gives a young tableau kind of formulation for the answer, but there is no quiver that corresponds to that.